Okay, so let's get started. Happy Halloween. Halloween is one of my favorite holidays, symbolic of 110 in various ways. In particular, I think we learn a lot of tricks in this class. We get a lot of treats too, so it's the perfect Stat 110 holiday. Speaking of tricks, a student from last year emailed me and told me that there's an open request at the Bureau of Study Council for someone to, quote, teach me all of Blitzstein's tricks. So that's probably going to be difficult to fulfill, so that's an open request with the BSC. But anyway, there are a lot of tricks. And a lot of treats. Okay, so today's going to be a very, very scary lecture, as befits the holiday. In particular, we're going to do, at the first half, we're going to do the beta distribution. And to give you some indication of how scary, terrifying the beta distribution is, I'll tell you a true story, which is that the first time I taught Stat 110, students were so clearly terrified of the beta distribution. I didn't really know why. Actually, it should not be scary. Okay, so I'll try to show you how it's not that scary. But for some reason, they were extremely scared of the beta distribution. Then on the final, I decided to be nice, and I didn't put anything involving the beta distribution because they were so scared of it. But then that really backfired on me because I think it was like students were seeing the beta distribution as like a ghost, and they were just seeing betas lurking everywhere. And when I was grading them with the TFs, there were just beta distributions popping up everywhere on the exam, even questions that had nothing to do with the beta. They were so scared, what if, is there a beta lurking here behind the corner? And there's just beta everywhere. So I think it would have been nicer if I just put like one easy beta question at the beginning, and then you kind of get that fear out of your system. So anyway, let me tell you what the beta distribution is. It's not scary, but for some reason it has been in the past, but it shouldn't be, okay? Well, what is it? It's a generalization of the uniform distribution. So far, the only distribution we know by name that is both continuous and bounded is the uniform, right? The uniform, let's say uniform from 0 to 1. Well, by definition, it goes from 0 to 1. And the PDF is just completely flat, okay? What if you wanted to generalize that and have, and other continuous distributions like the normal goes from minus infinity to infinity, exponential goes from 0 to infinity. What if we want something that's still bounded between 0 and 1, but is not just flat? Well, by far the most widely used distribution that meets those criteria is called the beta distribution. And it's not one distribution because it has parameters. So it's a whole family of distributions, which we call beta AB. So it has two parameters, A and B, where A and B are any positive real numbers. Okay? And it takes values between 0 and 1, as I said. And let's write down the PDF. The PDF is proportional to x to the a minus 1, 1 minus x to the b minus 1 for x between 0 and 1, 0 otherwise. C is a constant. So this is the normalizing constant. Okay, so one question we'll have to deal with is, can we actually integrate this thing dx from 0 to 1 so we can figure out what c has to be to make it integrate to 1? And that's a famous integral in math. That's called, if you integrate this, that's called the beta function. And it has a long history in math aside from its applications in probability and statistics. So we will talk about that integral at some point. But there's actually a lot that we can get from studying this without even knowing what the constant is yet. So here are just some facts, and properties. We've been emphasizing stories, right? Why write this down unless we have a story for it? The beta distribution actually has many stories to it, and we're not going to try to do all of them today, but we'll see more and more stories for the beta. But the most basic reason why betas are interesting is just that it's a flexible family of distributions of continuous distributions on 0, 1. And by flexible, I mean that as you vary A and B, you can make this take different shapes, right? So just for a couple quick examples, if we let A equal B equal 1, then this whole thing goes away. We just have a constant, so that's just the uniform distribution. So it is a generalization of the uniform. So the PDF would just look like that. But we can let A, we could let A equal 2 and B equal 1, for example. A and B they don't have to be integers either. It can be any positive real numbers. Okay, we could go A equals 2, B equals 1. This term is gone. Then we just have X, so we would just have something that, increases linearly up to 1. This is 1 here, right? It would just increase linearly. And, it's whatever makes the area of this area of the triangle has to be 1. So you figure out the slope. More interesting ones, if A equals 1/2 and B equals 1/2, you get something that looks like a U shape, kind of like this. And it's gonna, here's 1. And notice if it's 1/2, that's x to the negative 1/2. So as x approaches 0, it's gonna blow up. So this is going up to infinity over here. And as x goes to 1, this term is gonna blow up. So it's asymptotic like that. So you can get something like that. Okay, and if you let A equal B equal 2, then you'll get something that's just a nice looking upside down U shape, for example. These are just a few examples. You can plug in that's why I say it's flexible, that there isn't one shape that it takes. That makes it a useful modeling tool. So the main use of it is that it's often used as a probability for probabilities. That is, it's often used as a prior for a parameter that takes values between 0 and 1. So this is going back to, you had some homework stuff, and we talked a little bit in class about the Bayesian approach, where we treat the parameters as random variables. So if we have a parameter that's a probability, we know it's between 0 and 1, and we want to give it a prior distribution. The beta distribution is by far the most widely used choice in practice because it has a lot of nice properties. In particular, it's what's called the conjugate prior to the binomial. If you take stat 111, you'll be seeing a lot with conjugate priors. Obviously, I'm not assuming you know the term conjugate prior yet. I'll explain what this means. So this is foreshadowing 111 in a sense, but it's also just a 110 calculation that you should be able to do once you know what conjugate prior means, which I'll explain in a bit. Okay, and then it also has various connections with other distributions that we'll see later. So it's a very well-connected distribution. It has lots of nice properties and relationships with other distributions, and that makes it a useful tool. Okay, so let me explain what this conjugate prior thing means, because I just wrote that, but obviously you don't know what that is unless you happen to have seen that before. What we're going to do is generalize Laplace's rule of succession. So remember, that was the problem with, what's the probability that the sun rises kind of thing, where we assumed complete ignorance on the probability of the sun rising. Well, that's what Laplace did. Obviously, it doesn't have to be about the sun rising. We're not that ignorant. We have some problem where we're completely ignorant, and we modeled that probability using a uniform prior. Okay? So right now, we want to generalize that and say, what happens if instead of a uniform prior, we have a beta AB prior? And we don't even know what the normalizing constant is yet, but we don't actually need that for this calculation, as you'll see. Okay, so here's the conjugate prior thing, and I'll explain the word conjugate as this develops, but for the binomial. So here's the basic problem, which will look familiar, but we're generalizing, okay? So the problem is we observe a binomial given P. X given P is binomial. Okay? That's your familiar, our old friend, the binomial. if we're treating P as, this notation means if we pretend that P is known, it's just our friend the binomial, but P itself is unknown, and we're giving it a distribution to reflect the uncertainty of P. Okay? So in practice, the most widely used choice is some beta distribution. So we're going to let P be beta AB. Okay? So that's called the prior. That is our reflection of our uncertainty about P. That is, we don't know the true probability, so we're just treating it as a random variable. Before we actually, X is the data. X is what we get to observe. Before we observe X, we have a prior on P. That's our prior uncertainty. So this is not based on the data, okay? Then after we observe X, then we want to update our probabilities, right? Using Bayes' rule, right? So that's why this is called Bayesian statistics, because we're updating our beliefs based on getting the evidence, okay? So we want to find the posterior distribution. That is the distribution P given X. Now we get to know X, and then what's our updated? Originally, we have a beta AB. Then what happens after we're allowed to use X, okay? So how do we do this? Well, Bayes' rule. So this is one of these hybrid forms of Bayes' rule, right? Well, so let's, just to make the notation clearer, I'm going to write this as f of P given X equals K. You can also write this with a capital, just the capital X, under the interpretation that it's just shorthand for something like this. That is, we get to treat X as known. Okay? So this means, this is a posterior PDF, right? P is continuous, so it has a PDF. So this says, what's the PDF of P given that we get to know now that X in fact equaled K? All right, that's what that means. So by Bayes' rule, that's the probability that X equals K given P times f of P, that's the prior, divided by the probability that X equals K, where in the denominator, it's, key distinction between the numerator and the denominator. Obviously, you can't cancel these out. This one is a function of P. This one is treating P as unknown. This one is saying integrate over all P. So this one does not depend on P, because this is just going to be a constant with respect to P. It'll depend on K, but it won't depend on P because we've integrated out the P. So this one does not depend on P. All right, now let's just see what we have here. Probability of X equals K given P, that's easy. That's just n choose K, P to the K, 1 minus P to the n minus K. Now, f of P, that's just the beta density. So that's a constant, whatever that constant C is over there. We don't know what C is, but it won't matter. And P to the A minus 1, 1 minus P to the B minus 1, divided by the probability that X equals K. Now, seemingly to do a probability of X equals K, we would have to use the law of total probability. That is, we integrate and condition on P, and we can do that. But there's a much faster way to do this, which is just to look at the structure of what we have, up to proportionality. Okay, so I'm just going to write the proportionality symbol. That is, I'm going to ignore constant, and by a constant, I mean something that does not depend on P. Okay, so let's ignore constants. So actually, we can ignore the n choose K, because there's no P there. We can ignore C, because there's no P there. And we can ignore this thing because there's no P there. So all that's left is just this P to a power, 1 minus P to a power. So we have P to the A plus K minus 1 times 1 minus P, just adding the exponents, 1 minus P to the B plus N minus K minus 1. And then that immediately tells us the answer. So we didn't have to do any complicated calculations at all. I just grouped the P's together, the 1 minus P's together, ignored the constants. And then that immediately tells us that P given X, that's a beta distribution, right? It looks like a beta. There's some constant in front. Well, the constant is just whatever constant is needed to make this integrate to 1, right? So it's still of the form of a beta distribution. So this is going to be a beta with parameters. K got added. But if I write it this way, I'm just going to write a plus x, and then b plus n minus x. This is what the notion of conjugate prior means. The definition of conjugate, it's not just one prior, it's a family of priors. And that family of priors is called conjugate if we start with a member of the family. So we're looking at not just one beta distribution, it's the family of all beta distributions where you can change the parameters around. We start with a beta distribution, for the prior, compute the posterior, it's still beta, where these are the updated parameters. That's called the conjugate property. So this is the conjugate prior for the binomial. And this has a pretty intuitive interpretation that if we think of x as the number of successes and n minus x as the number of failures, the way you can remember this result and understand it intuitively is pretend that we had some prior data that we might have done an earlier experiment where we had a successes and b failures, and then we're just adding on. Now we have x new successes and n minus x new failures. Okay, so it stays in the family. That's computationally very, very nice. That doesn't mean it's true in any sense, and there are philosophical debates about should you use conjugate priors and things like that. Is that the correct way to reflect your uncertainty? Things like that. But there's no denying that it's convenient. You can start with a beta, you still have a beta. You don't need to work out a whole new theory of some new distribution. So it's very convenient in this sense, very, very, very flexible. So this is a generalization of the Laplace rule of succession. That was the case where we let this be beta 1, 1, which would be uniform. Okay, but the same thing works. So next time we'll derive the mean and the variance of the beta, but you can already see that that's going to be kind of nice too, because just stare at this density. I won't write it out now. We'll do this next time. But just to have some intuition for what's going to happen, look at this density. Suppose we wanted to compute the expected value of x. Then we're just going to integrate this thing with an x in front, right? Just definition of expected value. So we can combine this x, a minus 1, we'd have x to the a. It looks like a beta again. So once we know the normalizing constant, we can immediately write down the answer. What if you wanted the second moment, which you would use to get the variance? Then by Lotus, you would be putting an x squared in front, right, to get the second moment. X squared, x to the a minus 1 is x to the a plus 1. It still looks like a beta. So once we know the normalizing constant, we can immediately write down the answer. So it has very, very nice properties in that sense. All right, so let's not, we're not going to do the full normalizing constant today, but I wanted to do one important special case, which is the case of how do you get the normalizing constant in the integer case, okay? So the a and b don't have to be real numbers, but let's assume that we have integers up there. So another way to phrase that question is, here's what we have to do. We have to integrate from 0 to 1 of, let's say, x to the k. I'll write it in a way that looks a little more reminiscent of a binomial, but it's the same basic thing. X to the k, 1 minus x to the n minus k dx. I want to do that integral where now we have integers, non-negative integers up here. K is an integer between 0 and n. We want to do this. Well, okay, so if I first gave you this integral, you might say, well, use the binomial theorem, expand this out, multiply this whole thing out, integrate every term, and try to simplify. And it would be very tedious. Okay, so let me phrase this question a different way. Find the integral of x to the k, 1 minus x to the n minus k, without using calculus. So my favorite calculus problems are the ones where you don't have to use calculus. And so that sounds impossible. That's actually one of Bayes' most brilliant ideas. Bayes' rule itself, as we saw, you just write down the definition of conditional probability. It's just like one line, you get Bayes' rule. But Bayes also had an argument, 1760-something, he did this integral without using calculus. So I wanted to show you his argument because it's very beautiful, but it also gives us the normalizing constant for these integer cases. Okay? So what does it mean to do it without using calculus? Well, we're going to use a story. And that story is called Bayes' Billiards. Okay, so this becomes a little bit nicer if I put in an n choose k here. That's, you know, I'm just multiplying by a constant, so we could always adjust for that later, but this looks a little nicer. All right, so here's what Bayes did. He said, consider that we have n plus 1 billiard balls. That's like, you know, if you're playing pool. This is exactly Bayes' argument in the 1760s. He said, take n plus 1 billiard balls, and then you can do one of two things. You could either, originally they're all white, that we have, and they all look the same. And then we paint one of them pink. So now, at this point, we have n white balls and 1 pink ball. Okay, that's something we could do, and then throw down the balls, throw them on 0, 1 independently. That is, we're just positioning them. You know, we have the number line from 0 to 1. Here's 0, here's 1. And just throwing all the balls down, and, you know, you get some arrangement. Here's some white balls here, and maybe you know, the pink ball has to land somewhere. Maybe it's there. This is just an example. So we have IID uniforms. Okay? So that's the first story. Here's an alternative. So here we painted the ball first. We painted one ball pink, threw them all down. But another thing we could do is throw all the balls down at the number line and then paint a random one pink. So first throw, then paint. Then paint one pink. Okay? Now, if I just showed you this picture and didn't tell you where that picture came from, you would have no idea whether it came from this story or this story, right? It's completely equivalent procedures. Why should it matter whether you painted it at the beginning or the end? It doesn't matter. The final configuration is going to have the same distribution. All right? So the key to the argument is that these two ways of generating a picture that looks like this are completely equivalent. That tells us the value of that integral. Because now let's just let x equal the number of balls to the left of the pink one. Which I denote like that. Okay? That's x. So in this picture, x equals 3, for example. Just count how many are to the left. That's going to be some integer between 0 and n. All right? Now, according to this first story, it doesn't matter what order we throw the balls in, so we may as well throw the pink one first, then condition on where that is. And so we want an expression for the probability that x equals k. That is, there are exactly k white balls to the left of the pink ball. So by the law of total probability, we should just integrate probability that x equals k given p f of p dp, where this is just representing where p for pink and p for probability, where is the pink ball. Okay? And so that's something we can write down easily, because f of p is just 1, because we're assuming it's uniform between 0 and 1. Probability that x equals k given p, that's just a binomial, because we define success for the white balls. Success is defined as being to the left of the pink ball. Failure as being to the right. So we just want to count the number of successes. That's simply a binomial. And choose k, p to the k, 1 minus p to the n minus k, dp. Notice that that's the exact same integral we had. We changed the dummy variable x to p. On the other hand, we're running out of space here, but on the other hand, we can just write down the answer. Because from this second story, this is story 1, this is story 2. Story 2, I first threw the balls down, paint a random one pink, equally likely. So it's equally likely that there's any valid number of white balls to the left, I'm just paint the pink one anywhere. So all numbers from 0 to n, integers, are equally likely, so it must be 1 over n plus 1. So that integral is just 1 over n plus 1, and you can write that down just by looking at the picture without actually doing integration by parts or expanding things out or term by term, all that stuff. Okay, so that argument gives us the normalizing constant for some cases of the beta. Next time we'll do the general normalizing constant and see some of the connections to other distributions. All right, so we have one other very scary thing for today, which is finance. We have a special guest today, Stephen Blythe, who teaches Stat 123. Just to briefly introduce him, 123 has gotten better reviews from people who've talked to me about than almost any other course I can think of. There are a lot of students who told me that when they went and did finance internships, they felt way better prepared than their fellow interns because of having had 110 and 123. It's kind of a unique, just to tell you very briefly a little bit about Stephen's background. He got his PhD from this stat department here, so that's a proud claim to fame for our department. He then taught at Imperial College London. He has many years of experience working on Wall Street, and now he's managing director at the Harvard Management Company, which is responsible for managing a large portion of the Harvard endowment. So I think it's definitely true that at Harvard you will not find anyone else with the same combinations, both of practical experiences as well as academic training, just combining actually having been on Wall Street for years as well as having a PhD in statistics. You won't find that in any other Harvard course. I don't actually think you'll find that in any other course in the entire country. So we're lucky to have that course, Stat 123, which is not offered this spring, but it will be offered next year. And so Stephen didn't want to miss out on your group. So take it away. Let's all welcome him, and let me give you the microphone.
All right, well, thank you to Joe, and thank you all for giving me 25 minutes of your time. It's always a pleasure to talk to Stat 110. I'm here for a couple of reasons, really. Firstly, Stat 123 that Joe mentioned is a reasonably new course here at Harvard. I'll be giving it for the third time in 2012-13. So wanted to give you a little bit of flavor of what it's about. But secondly, Stat 123 has one prerequisite, which is Stat 110. So you all here are my eligible receivers, so to speak, or eligible to take the course. And I wanted to give you a little bit of its flavor. Apologize for the seniors in the class, if there are any who won't be able to take the course, but I hope the next 20 minutes might, even for them, be intellectually appealing. There are going to be a couple of brain teasers that might make you think a little bit about probability and its relationship with the financial world. Probability is, to borrow a phrase, the soul of finance. It's the sort of theory that underpins most of quantitative finance, and hopefully I will show a little bit about that today. So for those of you who enjoy this course and want to see what I think is a rather intellectually appealing use of probability, which is also very real-world oriented, that is what Stat 123 is about. Just one further word on prerequisite. Stat 110 is the only prerequisite. You don't need to know anything about finance to take Stat 123. The whole of quantitative finance was essentially built by people who knew nothing about finance and still don't really. It was built by probabilists and mathematicians and statisticians and physicists, a lot of physicists who moved to finance when the original Super Collider got canceled in 1993, and then they all went to Wall Street and built quantitative finance. So you don't really need to know anything about finance. Obviously, if you're interested in a financial career, it may be appealing, but Many students have flourished in Stat 123 without any interest in a financial career. So we've had people who wanted to go to Juilliard or play professional soccer, but are just interested in, some ways, a new way of thinking, a new way of reasoning about uncertainty, which uses probability to a great degree. If finance, you have a visceral dislike to finance, that's totally fine, but probably is not worth taking Stat 123 if that's the case. I did get a couple of comments about Stat 123. Finance is all about making money. I don't want to, and of course, right? I mean, that is what finance is about. It's about money and the financial world. So if that's got a visceral dislike, which I totally empathize with, perhaps not take it. Okay, so let me tell you a little bit about the course. Let's write this down. Applied quantitative finance on Wall Street. Obviously, I'm thinking about dropping Wall Street for 2012-13. It's not the... now, a natural subtitle, actually, to this course. So there are many pejorative words in this title, but a natural subtitle is Applied Financial Derivatives. Okay, this course is very much about derivatives. So two natural questions might be, what is a financial derivative? And why is this a probability course? Why is this a stat course? Okay, so the two natural questions, and hopefully you can answer them together. So a financial derivative has nothing to do with calculus, or at least its definition has nothing to do with calculus. There's some calculus involved in thinking about and valuing derivatives, right? A financial derivative, the term derivative means derives from. Okay, so a financial derivative is a contract, so it's a bet, an agreement between two people whose payout at some maturity date is a function of, or derives from, okay, the value of some other random variable. So for instance, if I enter into a contract with Professor Blitzstein where he pays me $1 if the total snowfall in Boston is above 80 inches this winter, okay, that is a weather derivative, right? The $1 is a function of some other random variable, in this case, the number of inches of snow in Boston. That's simply what a derivative is. In financial, usually means the underlying random variable that the payoff is a function of is a financial asset. It's the price of a financial asset, and typically written S. So in finance, random variables are S rather than X, okay, because S for stock. So if you think S sub T is just the price of, say, Google stock in 1 year, that is a random variable. Okay, we don't know what it is. It'll take potential values in a year's time. Okay, and a financial derivative is simply something that pays off a function of that. Okay, for instance, G of S might be the indicator function above 500. So if Google is above $500 in a year's time, you pay 1, or you get 1 from your contract. Okay, you might, well, who cares about contracts like this? And we'll see particular forms of G. So a little later, well, G of S, right, a function of a random variable is another random variable. Okay, so we're going to get caught up in or use random variables. And it turns out, and this is one of the key results in finance, it's called the fundamental theorem of finance because it's so fundamental, is the price that you would pay for a derivative contract. So even just think about this weather contract. How much would you pay for that? Well, it'll be related to the probability of getting more than 80 inches of snow, right? It can be related to the distribution of this random variable. And it turns out what you'd actually pay for the contract is very, very closely related to the expected value of G of S, okay? Right? In fact, there's a very powerful result that says if I choose the random variable correctly and choose the distribution correctly, it is exactly an expected value. So expectation is going to be run throughout Stat 123. Well, you know how to do this. If you know the PDF of S, this is just what I like to call POTUS, I mean Lotus, right? Always get those confused, but it's just the integral of G of S, F of S ds, okay? All right, so Lotus is going to play a major part in quantitative finance, okay? Okay. That's not all there is to finance, but that's pretty much, when I arrived on Wall Street after, I actually TF Stat 110 here many years ago. I loved it. And it was about 25 people in the class then, so it was easier to TF. It was a great class. I arrived on Wall Street, and the first day I was on Wall Street, I was asked to calculate the expected value of a function. It was a bivariate normal. That was a function of bivariate normal, and they thought that was an incredibly hard problem. It's not trivial, but I thought I can do that because I knew how to calculate expected values. I did that my first morning, and they thought, wow, this guy's really good. He knows all about finance. But all I knew about was bivariate lotus, and that stood me in good stead for the rest of my career. So, all right. So here's a couple of I won't call these brain teasers because these examples are also interwoven with Stat 123. So I hope if you'll take them, you'll sort of echo this lecture will echo back, and you'll think, oh yeah, I remember that teaser. If you have any questions about the course, just before I get onto these, please feel free to email me and belie.that. And two of your TFs in this class, Bo and Jesse, have either taken the class or TF'd it or both. So feel free to ask them about it. Obviously, I've chosen them because they enjoyed it a lot. But that's okay. So here are a couple of brain teasers. First one that comes from foreign exchange. So foreign exchange is a fairly straightforward concept. So how much is a euro worth in dollars, right? So 1 euro trades in Europe is worth about $1.40 now. That moves up and down. It's sort of a stochastic process. And one pound, which is close to my heart, that's worth about $1.60. These are things that people care about, obviously, if you go traveling or if you're doing trade. And one thing you might care about is where are these things going to be in a year's time, right? How can I predict what the value of, say, a euro will be in a year's time? Okay, it's obviously of interest in the economy. You might think if you could actually do that prediction, right? If that prediction was actually possible, then the person who could do that would be phenomenally rich and would be infinitely wealthy and would have retired, right? So you might want to think it's probably impossible to predict. But anyway, suppose people try to, right? And you can do it in lots of different ways. You can build time series models. You can think about economies. But one thing you can do is just build a little probabilistic model. And that's what we're going to do here. A very straightforward one, which takes two states of the world. It's called a binomial model with two states of the world. So let's start off with, so this is foreign exchange, known as FX in the business foreign exchange. We're going to take a very simple world. We're going to say we're going to think about the value of 1 euro. Okay, and let's assume that right now it's worth $1. So the price of 1 euro is $1, just to make the math easy. So currently there's $1. Sorry, I can write down here per euro. Okay, the actual number is about 140 for those who, and I'm going to say, where do you think we think that is? Where do we expect this to be in a year's time? Okay, and we're going to build a very simple probabilistic model. We're going to say there are two possible outcomes. The sample space in a year's time has two states. One where the euro becomes worth more. Oh, go and yell it. Okay, so let's just say it's now worth $1.25, so euro is worth more. And one where it's worth less. Let's say 0.8. Okay, that's a random variable. It's got two states of the world. I'm actually going to assign probabilities to it. Let's make it easy to say half and half. All right. Okay. This is a pretty straightforward model. We just think it might go up, might go down. Okay. All right. Now we're going to ask the question, where do we expect it to be in a year's time? Well, we can do expectation very easily. So the expected value of a euro in a year's time, which I'll just write expected value of euro, right? So half times $1.25 plus a half times 80 cents. Okay, so that's easy. That's $1, 2.5 cents. So this is where I expect the euro to be in a year's time. It will have appreciated on average to $1, 2.5 cents. All right? Okay, so that's pretty straightforward expectation. Okay, so that's what we expect for the euro. Okay, so well, we know what a dollar must be worth, right? So a dollar must be worth 1 over that, right? Which if you do, that's just 0.9756, right? Okay, so that's straightforward also, right? If a pound is worth $2, $1 is worth 50p, pence, okay? That's true, right? So if a euro is worth $1.02.5, $1 is worth 0.975 euro cents. They're called euro cents also. All right, so that's foreign exchange prediction. That seems pretty straightforward. So we're done. But before we move on, let me just restate this model. All right, well, this pink chalk would be good at this stage, I think. I haven't had pink chalk before, but let's see if we can use this pink chalk. Let's just restate the model. Well, $1 per euro, that's the same as €1 per dollar. So let's just restate this model in terms of the value of a dollar at each state. So this is €1 per dollar. Okay. Up here, well, it's $1.25 per euro. Well, that's 80 euro cents per dollar. Okay, and then this one is €1.25 per dollar. Okay, same model, right? Haven't done anything tricky. All right, now where do we expect? Let's just calculate the expected value of a dollar under this model. Well, the states are still a half, so just calculate that. That's easy. And hang on a sec. I've predicted the dollar to be worth more now. $1 is now expected to be €1.02.5. All right, so hang on a sec. You're just walking into your boss's office and saying, I've got this good model that predicts that the euro is going to appreciate to $1.02.5, but hang on a sec, the model also says the dollar will appreciate to €1.02.5. So if you did that, of course, the dollar will appreciate and the euro will appreciate. You guess the response is you're fired. Now, how do we solve this? All right, that's the first one. Simplest probabilistic model you could ever have, right? A binomial state, and we've already come across our first brain teaser. And what's actually probably more intellectually troubling, exactly, I find intellectually compelling than that, it's very simple, is that the solving this, actually understanding what's going on here, is actually quite non-trivial, and we attack it 2 or 3 ways in Stat 123. So that's the first one. Okay, so second one is TARP. So this is, when I said this course is applicable, hopefully this gives some flavor of how this course is applicable about what really goes on in the financial world, and whether you're interested in it or not, it certainly is an important part of the US and the world. So TARP, back in 2008, for the seniors of you who arrived here in September 2008, October 2008, you know that was not a happy time for the financial system or banks or the Harvard Endowment for that matter. Obviously a lot of things were going on in 2008, and there is a great econ course called The Financial Crisis, which I recommend to those of you interested in that. So what I'm going to do is I'm going to focus in on one particular part of the financial crisis that was going on in October 2008. Now this is called TARP. TARP initially stood for Troubled Asset Relief Program. In the midst of all this financial crisis, there was a transaction where the US government, i.e. taxpayers, received from this private institution warrants. Okay. Now warrants, this has nothing to do with being arrested or the legal system. A warrant is a type of financial derivative, okay, called a call option. So they're equivalent to what's called a call option, okay. And what a call option was, or is, it was the following. So let me just write down what the government actually had. So the US government paid, I've rounded the numbers, but $450 million to Goldman Sachs, GS, and in return, okay, US government had the right, so the right is not the obligation, it's the choice, it's the option to buy Goldman Sachs shares for $125 in 10 years' time. Okay? It's as simple as that. Okay, they paid, and they had the right to buy, it was 10 million. So they had the right to buy it for $125 each. Okay, at the time, so this was in October 2008, Goldman Sachs shares were trading, were $95. Okay, all right, so you might ask, well, what was the government doing paying all that money to buy Goldman Sachs shares for $125 when they could have just gone out and bought them for $95? Right? Okay. All right, well, let's just think what the government has in 10 years' time. So, okay, if Goldman Sachs shares in 10 years' time are at 150, what's the value of one of these warrants, one of these options to the US? $25, right? Okay, because I can buy something that's worth 150 by paying 125 for it. So okay, if Goldman Sachs is trading at 100, what's the option worth? 0, right? Okay, so we can begin to see this function, this G function taking shape for this warrant, which is the same as a call option, just terminology. All right, this G function is max of the share price at maturity T. Here, T is 10 years. And what we'll call K, well, K is, in this case, 125. And K is called the strike price, okay, and 0. All right, so here is a particular form of G, okay. So the payout looks like this. So this is G of S. Okay, so if I know the distribution, the PDF of S in 10 years' time, I know the price of this warrant, right? So the warrant, the price, my board management very good, is just a lotus. Okay. Okay, so two things you might want to, well, two things to point out. One is the government decided that the cost of one of these options, if you work it out, is $45 per option. Where did that come from? Is the US government in the business of calculating probability distribution, probability density functions? Right? So that's one question, which we'll talk about in 123. The other thing just to note is the solution to this. It's just a lotus, right? If you think about it, it's actually not that tricky because you can just replace the limits of integration, get rid of your max, right? Okay? It's actually a fairly straightforward integral. The solution of that integral under particular form for the probability density function is a very famous formula, the Black-Scholes formula. Okay, so I like to think that you can get a Nobel Prize in economics just for knowing lotus, because that's what the Black-Scholes formula is. Okay, so thank you for your time. Appreciate coming here, and hope to see some of you next year. Thank you.